Good morning, all. I got a question here that is such a good question. It deserves its own video. We've never covered this on this channel, and it's one of those. It's really not obvious the things. Okay, this is called Minkowski space-time. Okay, so we're only obviously looking at two dimensions, right? And there's only a few rules. The one rule is that you're far away from a gravitational field because if you were not, this would be all warped and it would be general relativity. So this is special relativity. And this trap happens to everyone when you start studying this. It happened to me, I know, is that you look at this and it looks Euclidean and you think, oh, well, I know how to do that because that's what I've been doing. But it's not Euclidean. That's the problem. Okay. So here are two bases of vectors, and you see they're ortho-normal, like we're used to dealing with in Cartesian the space. But when you use what's called the Lorentz transforms, because you want to now move from, this is a rest frame, we want to move from a rest frame to a moving frame, and we're doing that as a percentage the speed of light. And what you see happens is these basis vectors change and they start scissoring toward each other like this. And the reason is that they scissor is because one of the postulates of special relativity is that everyone must agree on the speed of light. And it's drawn like this. It bisects these two axes, right? So when I start moving at a percent the speed of light, I have to make this distance between these the same. That's why they scissor like they do. Okay. And what I'm going to show you is the trap we fall into, and I did, is that you think these basis vectors are growing in length, right? And they are not. And here's why. This is not Euclidean space. This is hyperbolic space. And they follow hyperbolas. So watch them as we move, right? They're following hyperbolas. And in hyperbolic space, the length of that vector is the same as the length of that vector. And it does not look like that. I understand it does not look like it should be the same length, but it is, okay? And oh, I wanted to show you also that the coordinate lines, which the basis vectors are just a derivative of the coordinate line, right? They're just an operator. So the coordinate lines, they do the same thing. They follow these hyperbolas, okay? So let's go look at the math of this and try to understand what this actually means, okay? Okay, the question, it boils down to this. What are Minkowski orthonormal basis vectors? Because we're in what's called Minkowski space-time, which was worked out by the mathematician Hermann Minkowski, which was actually a teacher of Albert Einstein. So by definition, the metric tensor in a non-accelerating, they call this inertial, frame at rest, far away from a gravitational field is given as this. All right. So we've got the time, a GTT is ET dot ET is equal to 1. These off diagonals are equal to 0. And GXX is equal to -1. Right. This is by definition of Minkowski spacetime. Okay. So to calculate that new basis we were looking at in a moving frame, we use what's called the Lorentz transforms. Okay. Lorentz transforms. Excuse me. Okay, and they're given as this. So the red guys are the new basis vectors we saw moving, and they're given by these equations, and where beta is equal to the velocity you're moving divided by the speed of light. So it's a percent the speed of light. And gamma is equal to 1 divided by the square root of 1 minus beta squared. Okay, so this all comes from Lorentz transforms. All right, so let's actually look at what happens to convince you that those basis vectors are the same length whether you're moving or not moving, okay? So how do we find the length of a vector, of any vector? Well, we dot it with itself. Yes. So this is et dot et. Let's distribute these scalars because it makes it easier. So it gives us this. Now, we just said that. Now, these are the basis vectors of the non-moving frame, and we just said what their values were. So the cross terms, et, ex, and exet are 0. So we don't have to worry about those. So when we take et dot et, we get gamma squared et dot et. When we take this dotted with this, we get this. All right, let's factor out. Well, first, let's put in what we got. Et dot et was 1. Excuse me. I got something going on here. Ex dot ex was -1. Let's factor out a gamma squared, which is, and then we got 1 minus the beta squared, right? This becomes negative. And what is gamma? It's 1 over the square root of this. If you square it, the square root goes away and you get 1. Okay? Now let's do one of the cross terms, which is et dot ex. So this is et dot ex. We do the same calculation and we get 0. And you know by symmetry, ex dot et is 0. If it's a metric tensor, if that bilinear form is a metric tensor, it has to be symmetric or it's not a metric tensor. Okay, let's do ex dot ex. All right, here's ex dot ex. We go through the same exercise, and we wind up with this negative here. We factor it out a negative gamma squared. We put in what gamma squared is, and we get -1. So I know it is wacky, but the basis vectors, no matter how fast you're going up to the speed of light, when you get there, it's undefined. They are ortho-normal as long as you follow that this is true. And the speed of light is agreed on by everyone, and no matter what frame you're, it is true. Okay, I hope that helps. If it does not, let me know. I'll see you later.